I first thank the organizers for the opportunity to be here talking to you today about this work. This is one of the topics I've been studying in my PhD with my advisor, Professor Silvia Ferreira. Oh, no. With my advisor, okay, sorry. Professor Silvia Ferreira. We are part of the Complex Systems Investigation Group at Universidade Federal de Viçosa in the state of Minas Gerais. And we are using visibility graphs to study phase transitions. And I'll start with this flowchart to explain how we do that. We start running on a spreading dynamics that will be any kind of dynamics that you can generate a time series, right? But we choose to study spreading process. So we run a spreading phenomenon, a spreading process on the top of a network structure, right? Then you generate this prevalence time series. I will go into details what each step is. And from this prevalence time series, you generate visibility graphs and make complex network analysis in these visibility graphs. So just to emphasize something, when I will start talking about my results, I will talk about two kinds of networks. The one in which dynamic process is evolving, right here, and the visibility graphs, right? And the research question is something like that. Can I get information on the original network and the original process just by looking at the visibility graphs that I generate? Right? This is the research question. So I will start by this slide, showing you the models we studied in the network structures. Of course, I will not say, I will go into details of each one of this model, each one of these networks, but this is about all we have done. And what is interesting is that for each kind of model here, you have different interesting aspects of phase transitions, right? For example, here in this two-species contact process, we have a discontinuous phase transition. Here in this quenched contact process, we will have what they call the Griffiths phase, right? The rare regions, the Griffiths phase. So different interesting aspects of phase transitions in different network structures, right? So just to give an example of how we proceed, we have the contact process model. This model is known to perform an absorbing state phase transition, right? And is basically defined, and you have your nodes in your network, and that can be infected or occupied or susceptible or empty, right? And the infected nodes will replicate, will infect another nodes with this probability, and you can compute, or they also can heal. In our work, you use spontaneous healing rate fixed as 1. So you can compute across time, over time, this measure right here, ρ. This is the density of infected individuals, or the epidemic prevalence, right? So you will compute this, and using quasi-stationary methods, because eventually the system will occur in the absorbing state, right? When you don't have any infected individual, and it will be caught in this absorbing state, so you need to use quasi-stationary methods to generate this time series. So for each infection rate, that is the lambda, I will generate a time series here, right? And when I make the average of this time series and plot it against the infection rate, I will see that my order parameter, that is the average prevalence, will perform a continuous phase transition. As you increase the size, here I'm doing this in a square lattice, right? But any kind of homogeneous network, it will be fine. You'll find this kind of transition here. As you increase the size of your network, you see clearly the critical point. You can also calculate, for example, the susceptibility, and the susceptibility will peak in your critical point of the transition. So I'm interested in studying different time series in different regions, in the subcritical region, in the supercritical region, and in the critical region especially, right, in the critical point. So once I have generated this time series, I will map them onto networks, right? So Lacaze and colleagues in 2008 have proposed this very simple method to do that, to map time series onto graphs, using a simple geometric criteria, right? So if 2 points in your network have visibility, they see each other, you connect them in the generated network. So instead of doing time series analysis, we'll be doing complex network analysis, okay? So for this time series I showed, I'll generate visibility graphs and study them. Well, in the beginning of this work, we made a lot of different measures of these visibility graphs, but one of them caught our attention, especially. That is the degree correlations. The degree correlations of a graph will measure how the nodes are connected to each other, right? If the hubs are more connected to the hubs, or the hubs are connected to low-degree nodes. So you have different behaviors for these curves that I actually can measure the degree correlations using this average degree of the nearest neighbors, right? Then I calculate this K and N here, average degree of the nearest neighbors, using this. And if I plot it against the degree of each node, I'll have this kind of curves. Just remember, this here I have two visibility graphs generated by the critical time series of the contact process in these two networks, a square lattice, a lattice degree with dimension 2, and a random regular network. And I have these degree correlations for the visibility graphs. So if you look at a very known measure, which is the degree distribution of the visibility graph, you see that the curves are different, but these curves does not show us as much information as the degree correlations show us, right? Because here I have the original networks having the same number of neighbors, right? 4 neighbors. And they give me 2 very different behaviors, right? We explain why the square lattice does not give me this disassociative large degree signature here in the paper we published last year. But I wanna talk a little bit about this signature here, the large degree disassociative. This signature we observed only in the critical time series, right? I mean, the time series we generate from the critical value of infection rate. So we can say that the visibility graph is a good measure, is a good tool to use calculating the degree correlations to distinguish between time series that are in different regimes. In different, for example, in the critical, you have the signature, and the off-critical regimes, you have just assortative patterns. And it holds very well for different cases. For example, here we have a 4-dimensional lattice, and here we have the same situation for a random regular network, the contact process in this random regular network. Off-critical, assortative. Critical, disassortative. Okay? So far, we have studied just the continuous phase transitions. But what happens if you have a discontinuous phase transitions? What information the visibility graph can give us? So for that, we studied the 2-species contact process. That's very well explained in this paper for Guilherme. And in the 2-species contact process, you have that if just one species is occupying the site, we have just the simple contact process I showed you in the beginning. But if there are two species occupying one site, they will interact symbiotically, right? Then the healing rate will be lower than the healing rate of a single occupied. So, as you vary, as you change this parameter here, mies, you can say if your phase transition will be continuous or discontinuous, right? Just varying this parameter. I'm not going into a lot of details on that, but the fact is you can have both transitions in this model. So the visibility graph gives us that. You have, when you're looking to the continuous phase transition, this curve for this value, and you do the visibility graph for this value of infection rate, will kind of recover what you have in the simple contact process. But if you try to approach of the transition point in the case of discontinuous phase transition, you can approach from the right or the left here of the discontinuity, and you will not get the dissociative behavior. It will get only the off-critical signature, as we expected. Okay? So, in this paper here, we have other discussions about how to understand the criticality of your process using visibility graphs. But in the follow-up of this work, we are interested in studying another stuff. For example, for the transition to happen, you have, for the other parameters to go from an inactive phase to an active phase, you have activation mechanisms. And if the process, for example, the contact process, or any kind of homogeneous network, this activation mechanism will be collective, okay? So in the sense that each part of your network will contribute more or less the same for the transition to happen. But if you have localization in your network, heterogeneous network in general, the activation mechanisms will be different. So we are interested in studying the localization, the activation mechanisms using visibility graphs. So I'll show you just two examples. The most extreme examples, we studied a lot of stuff in the middle of these two extreme examples. But I'll show you the most delocalized process we could think. That is the SIS model in an annealed network. For example, annealed networks, the connections are not even made. The connections are just probabilistic, right? So you don't have a structure. If you don't have a structure, the only mechanism possible will be collective. So what you see is, as you increase the size of your network, that strongly dissociative signature will emerge, right? But it holds for quenched networks as well. This UCM model generates power law degree distributed networks. In our case, we're using this power law with this exponent. It's a scale-free network. And the contact process in this network gives us the same signature, right? Delocalized. But if you look at another extreme example, that is, you have a random regular network with just one hub, or with size n squared. You put in the middle of your network, your homogeneous, you create a region, a rare region of strong localization, okay? And here I brought the susceptibility in the case of the SIS in a random regular network. With the hub, you see multiple peaks. And I remember what happens in the SIS, or the contact process, in a random regular network. I have the dissociative pattern. And for this case, the transition point is the same as in this case, right? The transition is still here. It still exists at the same value of infection rate. But if I calculate the visibility graphs for this point, for this infection rate, I does not recover this pattern anymore. So the message is that if you have your time series, this work is just theoretical, right? We don't analyze any kind of real data. But in real life, if you have your time series and you find assortative degree correlations of your visibility graph, you have two options. Or your time series is off-critical, or if you are sure that it's critical, you have another measure that says to you that it's critical, it's probably because there is some kind of localization that is making harder to see the criticality in your model. So, just to conclude, what we saw is that the visibility graphs can be a good tool to investigate this difference between critical and off-critical time series in the first place. The second point is that this only critical dynamics feature that large degree disassortative. So the method has never given to us a false positive so far, right? So, and this, we are working on that at this very moment, that localization destroys criticality, and that, for example, at least for the models we studied, we see that the degree correlations of the visibility graph is able to capture this. So I'll let you with our paper we published last year. I hope the follow-up is out soon. And thank you very much for your attention.
We have time for a quick question. Okay. Thank you, Juliane.